Okay, no messing around today, no jokes. We're just going to we're going to just dive straight in. What I want to talk about today are some basic structural principles so that you can kind of maybe appreciate the way that I look at furniture a little bit. I mean, I'm still telling that big story, and this is a part of it. It also means that I can use some of this jargon and use some of this language that I'm going to try and introduce you to throughout my videos, and it will hopefully make a little bit more sense, you know, by having some sort of introduction to engineering principles. That's kind of what I want to achieve. And in order to achieve it, I'm just going to keep things basic, keep things simple. I'm going to try not to go into too much detail. I mean, I could talk about this stuff for probably ages. And that's not going to make a good video. So, you know, if you're an engineer or someone with experience in this field, you know, please don't hold it against me. This is just, I'm being a little bit liberal because I want to keep it brief. just want to keep it very, very simple. So to start with, I just want to go through the fundamentals, like units. What do we measure stuff with? And the first thing I want to talk about is units of measurement for distance. Now, if you're in the UK or Europe, and to be honest, much of the rest of the world, the units of measurement that we use for distance, for large units, with large measurements, we would use meters, and for small measurements, we would use millimeters. That's what we use. If you're in the great US of A, then you'll probably use feet and inches. I mean, if I'm being completely honest, you know, my dad still uses feet and inches on a building site. You know, it's not universal. People still use feet and inches. I think if you're doing anything scientific or, you know, mathematical based, you'll generally tend to use meters and millimeters. And I'm not here to tell you that using either of these units is wrong. If you're comfortable with using feet and inches, then I would highly recommend just continuing using feet and inches. You know, that's your deal. That's what you've probably been brought up to use. There's probably very little chance to change. And if it works for you, if you can understand it and make it work for you, then there's no way that I need to tell you how to do it differently. For me, I use meters and millimeters. It's just because they're much, much easier. And I want to demonstrate that. And the way I'm going to demonstrate it is just by making a little table. And on one side of the table, I'm going to put millimeters. And on the other side of the table, I'm going to put inches. Now, for small denominations of inches, i.e. something that's smaller than an inch, people tend to notate that as fractions. That's how it tends to get notated down. So what I want to do is I just want to put down a few dimensions of distance in inches with fractions and show you what it looks like. Yeah. That's what a series of dimensions in my mind looks like if you're using small dimensions. I mean, this is really what we're being specific about. In carpentry and in woodwork, we're looking at small dimensions, small things. So how we measure those small things is really important, and that's really what I'm trying to demonstrate here. So what I want to do is I just want to quickly convert all of these dimensions into their millimeter equivalent. Okay, so these mean the same thing. This dimension in inches is the same as this in millimeters. From my perspective, just looking at these two sets of numbers, you know, just looking at inches, for example, this looks like just a complete nightmare to add together. As a semi-mathematician, I would look at this and say, okay, what I want to do is I want to convert everything with a common denominator of 16. So everything over 16, I'd try and convert all of these into a complete fraction over 16, and then I could add them together. And I know that there's a button on the calculator that will do the job, but it involves a heck of a lot of button presses. Like, it just seems like a complete nightmare to me. You know, if you're familiar with feet and inches and you've been doing this a long time, that might look sensible to you and you might be able to just do it in your head. But for someone like me, and you know, probably for quite a lot of people who are not familiar with feet and inches, you know, if you're kind of on the fence about which one to use, that you'd probably look at that and think, oh, that looks like a nightmare. How do I do all of that? And I agree, and I deal with numbers quite a lot. Whereas in millimeters, we just have a string of numbers which the calculator will do quite happily, really easily. So, you know, for me, millimeters, I don't understand how anyone can do this, but if you're familiar with it, I'm not even going to comment. I'll leave you alone. If you're on the fence, definitely use millimeters. All of you, if you're just using inches, I would recommend trying out millimeters at least to give it a go, because it is easier, and in the long run, it's going to be more straightforward. But if you're stuck in your ways and you're happy, I'm not going to tell you to do it any differently. So that's units of dimension for distance, and let's have a chat about units of dimension for units of mass, not dimension of mass, that's rubbish. Units of mass, I'm trying to be specific. Right, that's better. And for large units of mass, UK, Europe, most of the world, we tend to use kilograms. And for small units of mass, we use grams. And if you're in the Great US of A, you're probably using pounds for small units of mass, and you're probably using ounces for pounds for large units of mass and ounces for small units. Now, I'm an engineer, so for me, mass isn't important. Mass is just the measure of amount of stuff in a thing. In order to get to a force, we need to put that mass into a gravitational field. The formula for force is mass times acceleration. That's the formula. And in a gravitational system, the speed of acceleration is just gravity. So the way we get from mass to a force, and specifically when we're talking about mass, we mean weight. We times these numbers by gravity. And the large units of weight that we use are kilonewtons, and the small units of weight that we use are newtons. Now, for most people, those are the same thing. And the reason is because gravity on planet Earth is more or less the same everywhere. So when we times this by this, it doesn't actually change the result fundamentally. These are still proportionally relative back to these pounds and ounces. The only time that this matters is if you were designing something not on planet Earth, if you were designing it on some other planet. So in brass tacks scientific terms, pounds and ounces only exist on planet Earth. They don't exist on any other planet. Whereas kilograms and grams exist in the whole universe. That is the scientific principle behind why we have two different things here for something that probably means the same thing. And as I said, the reason why it probably means the same thing to you is because we only really deal with mass on planet Earth. And so mass and weight are basically interchangeable because gravity is consistent, constant throughout. Okay. Now, in order from a structural perspective, we tend to combine these into something which we call stress. Now, if we take a structural member, I've got a piece of wood here, and we apply a force onto the ends of it, so essentially putting this piece of timber into tension, then we define the stress by the force divided by the cross-sectional area of the member we're talking about. And we are assuming that we're going to get an even distribution of stress through the member, and that isn't necessarily the case. But from a stress perspective, that's how we calculate it. We divide the force by the cross-sectional area. And by extension, by logical extension, if we doubled the surface area, we doubled the cross-sectional area, so this thing was twice as thick, then we would be achieving, with the same force, we would be achieving half the stress. And that's how it works. And that's generally how we rate materials. Like, you've probably heard tensile area strength or something of that equivalent. And you can compare different materials with that number. So for those sorts of units, for units of stress, we have a new system. For large units of stress, we use kilonewtons per meter squared. And for small units of stress, we use newtons per millimeter squared. So that's essentially the force divided by the area. That's, You know, that's what I was just doing, force divided by the cross-sectional area of the section we were discussing. And in general terms, we don't generally tend to use this for structures. We generally tend to say that this is a pressure rather than a stress. And the reason is because not many structural members have a cross-sectional area that is in meters squared. It's normally in millimeters squared. So this is more pressure. We generally use stress, newtons per millimeter squared. Now, the reason why I bring it up is because in America, if you're an engineer, you are probably dealing with pounds per square inch. Now, first up, that's an inch squared. So we have to take one of these fractions and then we have to square it. And that's not including the fact that there are 12 inches in a foot. And that's an awkward number to deal with. So just dealing with the unit of dimension in inches is a pain. Then we have pounds and ounces, and there's, 16 or 18 ounces in a pound? I don't know what it is. I don't deal with it. So in order to get to this number, you have to take this number, which is awkward, square it, and then use another number from over here, which has got like a factor of 18 or 16 or something in it, and you arrive here. Oh man, if you're an engineer in America, I generally don't understand how you work with units like this. It completely blows my mind. But you know, from the purposes of this workshop, we probably aren't going to be dealing with much of this. There might be a few occasions where we deal with some of this. We are definitely not going to be dealing with stress. You know, the only way we're going to deal with stress is if I start testing materials. I'm not going to be dealing with that. That's really hard and complicated. All we're really going to be dealing with is distances. I just wanted to give you an idea of the fundamentals of what I kind of use for my structural engineering stuff. So those are units. Let's have a chat about load types. There are two basic load types. There's a UDL, which is a uniformly distributed load. And then there's a point load, which we refer to as a PL. That's how we would note it down. And if we had a beam, the way we would draw that on that beam is as follows. We would have like a squiggly line like so. And the best way to imagine this is that on this beam, you put, I don't know, a foot, sod you feet and inches, 300 millimeters of sand over its complete length, so that all of the load is evenly distributed over its complete length, i.e. a uniformly distributed load. Then that's what that would be. And this is a fairly common, I do this all the time because, you know, floor joists and beams and stuff, we have a uniformly distributed load we need to take for the floor. So this is fairly commonplace. And then we have point loads, which we would notate with an arrow like so. And a point load is something that's very, very high load that's being exerted on a single point. You know, it's a point load. That's kind of, you know, I don't really want to make it obvious, but you know, that's how it is. The next thing I want to talk about is support conditions. And there are two support conditions. We have pinned, which we generally notate with a triangle like so. That's how I've done these. That's a pinned support beam. That's how this works. And the other type of support would be a fixed support. And we would notate that like so, with the beam sticking out the side. So this situation that I've just drawn here, this is a cantilever. And you've probably heard of a cantilever, you probably know what it is. From a technical perspective, what a cantilever is a fixed support condition at one end and no support condition at the other. Now, the way to visualize these two pinned and fixed support conditions is to take this beam and imagine that we're supporting it with just the top of your fingertip. So the thing, if we imagine the gravity is coming down the screen, the beam itself is free to rotate. That's how we think of a pin support. You know, it's pinned. If you imagine we put a single bolt through the middle of it and then bolted that to some other member, it would rotate around that bolt, and that's a pin support, and that's okay. Like, it might seem like that's the bad thing to allow it to rotate like that, but it's all allowed for in the maths. That's kind of part of the deal. The other way to visualize a fixed support condition is not supporting it with your fingertip, but it's to grab it with your whole hand. So if we try and push down on here, it's being prevented from moving by the action of my hand. That's a fixed support condition. And we can juggle these two together. So if we say took this fixed cantilever and we put a support at the end, but that was pinned, that would be what we call a propped cantilever, and that would be something like this. So because we've got a fixed support condition, the beam it deforms differently because, you know, as a result of having a fixed support, whereas what we'd normally do for beams is we'd normally just assume pin supports at both ends. So any force that's exerted on this beam just gets transferred to one of these supports, and the beam is technically free to rotate at the supports. That's how we. That's all in the maths. That's all allowed for. Now, one thing to note is that we are always, as engineers, we are always trying, as structural engineers specifically, we're trying to maintain an equilibrium of force. And the reason is because when something is out of equilibrium from a structural perspective, it becomes, technically speaking, it becomes a mechanism. And we as structural engineers, our first job when we're designing structures is to prevent the formation of mechanisms or collapse mechanisms specifically. So when we have a system that moves, it's bad. So let's just imagine, you know, moving buildings. No one likes moving buildings. Let's just imagine this cantilever situation again. What about the support? Let's just imagine that we didn't put a fixed support condition at the end. Let's imagine that we just supported it with our finger. So gravity's still acting down. When I pushed down, it would just move freely. There's nothing there to stop it. That is a mechanism. That's an out of balance load. There's no equilibrium being developed between the forces being applied to the member, and as a result, it's moving and it's a mechanism. That's, you know, on a very basic, simple term, that's what we as structural engineers, our first job, before we do anything else, we are looking for collapse mechanisms and how do we prevent them. Now, as I said, with most beams we just do pin supports, and the reason is because for these fixed supports it's really, really onerous on the structure. You know, this is quite a lot of load to go back into the structure, so we try and avoid this situation when we can. You know, the only time we really use it is for these cantilevers. You know, we can do beams, this is what we would call a built-in beam with fixed supports both ends, and we can do that, but it would just cause so much work on the rest of the structure that it's just easy just to assume it's pinned. That's how it works in engineering. You know, we're so afraid of these mechanisms. We'll go overboard. We'll try and keep things simple. You know, if we assume that we've got pin supports, then this thing can't really provide any. It's got no real action on the rest of the structure. I'm getting technical. I'm getting too into detail. Right. Let's forget I just talked about that because that's not relevant to what we're talking about here. So that's as a quick rundown. We've got, you know, units of stuff. What the stuff, the reasons why I use them, and, you know, how to calculate that, and we've got the different kind of loads and support conditions that we can use on a structure. That's really what I wanted to get done on this first page. Let's move over to a second page and deal with some other stuff. Okay, so there's a few different ways that these forces can interact with a structural member. And I'm just going to go through each of them individually. So, first type of load would be an axial load. And there are two basic types of axial load. If we've got a structural member, let's just draw a structural member. So, an axial load is directed in the principal direction of the member. It's either it's directed with it along its length. So there are two basic types of axial load. There will be a tensile load, which would kind of, as I tried to demonstrate earlier, it's kind of pulling it apart. You know, we're exerting a force outwards on this, and that's what those arrows mean. And then obviously the alternative would be compression. So the force is acting in on itself. Those are the two main axial loads that we deal with members. And for tension, As I said earlier, you know, tension is like a universal benchmark for different materials and how they perform under force. The tensile strength is just such an easy test to make. It's just an easy test to perform that it makes a lot of sense to define a member by a material by its tensile strength, and that way we can kind of compare how different materials perform. And I'm certain that you would have heard of that. And the other main reason is because with tension, there's only one real mode of failure. You know, the only mode of failure is for this thing to yield, to pull apart from itself. As a mode of failure, it's just such a fundamental mode of failure. It demonstrates the real fundamental nature of the material, and that is why we use it to define different modes of failure, different materials, sorry. Now, for compression, we have a different mode of failure, and that is buckling. Now, I'm not going to be able to exert enough force on this member to show you buckling, so let me go grab a different piece of wood. I went and got a piece of wood and I tested its compressive strength twice and I broke it both times. It turns out this wood doesn't like bending very much. That's a real shame. I don't have a piece of wood that can demonstrate it, that I am able to compress to a certain extent. All right, let's do this differently. So I'm hoping that buckling is something you're probably aware of. When you compress something, its natural reaction is to want to bend outwards. And this is a really difficult mode of failure to analyse because it really doesn't have much to do. It doesn't have much to do with the material that it's made of. It's more to do with the shape and geometry of the section that's being used. The fundamental strength of it obviously does come into action because it snaps. You know, it doesn't yield like the way that a tension does, but it's different. So. The things that matter to compression have nothing to do with tension. So for tension, we don't really care about how long this member is. You know, a cable on a bridge is hundreds of meters long. You know, potentially on some bridges, I'd imagine they would be, and it doesn't matter that is the case. The tensile strength is exactly the same. But for compression, if you double the length of the member, then you get a real fundamental reduction in its strength. Probably something on the order of, I don't know, somewhere between 4, maybe 6 or 8 even, you know. You'll get a member that's twice as long under compression will be 4 times less strong or 6 times less strong, that sort of order of magnitude. This buckling is really detrimental to structures, and to be honest, it took a long time for the engineers of the past to work this stuff out. You've probably heard of a phrase, and it goes like this, is every force has an equal and opposite reaction. It's something that engineers we live by. And the reason is because although this is in tension, so we're pulling it apart, if we just say we had a building here, then the force this building would have to counteract would be in the opposite direction. So this cable is in tension, it's pulling itself apart, but on the structure it's trying to pull itself away, and the reaction the building needs to maintain in order to keep that in place is the opposite of this force. And that's how that phrase, every force has an equal and opposite reaction, that's how that phrase works its way into structures. So in much the same way in compression, if we had a structure down here, then the reaction to this force would be the opposite. It would need to go downwards. We'd be pushing, if we imagine we're pushing downwards onto this, that's pushing down onto the page, but the force in the member is going up. So those are axial loads, tension and compression. They're the only two we need to worry about. But we also have our shear loads. And this really only, I suppose it occurs in 2 different situations. So if I'm holding this, a shear load is something that's very, very close to the support, and it's trying to shear off the piece of wood. You know, that's what a shear load is. The You know, if you've got a bolt is a prime example. A bolt is generally designed purely for I mean, it does do other things, but it's mainly designed for shear. That's what it's trying to do. If we imagine we've got a column and connected to that column is a beam, then all of that force that that beam is supporting is being transferred into that column by a downwards load here. And the column is required to counteract that the exact same way that this is working. Every force has an equal and opposite reaction. So the shear on the beam comes downwards, and the shear from the column, the opposite reaction goes upwards. And that's what I'm trying to do here. I'm pulling down with one, pushing up with the other. That's a shear load. That's just how it represents itself. And so the other way that a shear load, and this is maybe a little bit less frequent, but is in torsion. So let's just assume we've got a tube. Let's give it some thickness. A torsion would be, if we try and, I mean, it's a twist. Some of these things are just so natural that we talk about them that it's difficult for me to talk about them technically without getting in the way of your pre-existing understanding of what they might be. So a torsion is two opposite twists on the same member. So instead of going up and down, I'm twisting it one way or the other. Imagine like a Chinese burner. If you ever had one of those as a kid, that's what a torsion is doing. It's trying to twist the material. And in technical terms, torsion is the only example of a pure shear. It's the only time where the reaction is only in shear. When we have a situation like this, there's a small moment caused. I'm going to talk about technical terms just for a second. When we design this stuff, we assume that everything's got we assume everything is on the center line. So we tell when we do a piece of structural design on a piece of software, we basically just draw we have two dots. Those are generally coordinates. We join them with a line, and then we kind of tell the computer what that line actually means, so that represents the beam that we're using for that line. It doesn't actually exist in the computer as a collection of shapes. It just exists as a line. So when we define that line, we want to use the center line. If we're using the center line, then we actually, because the pin is here, we actually generate a small amount of moment here. I think I've probably gone too far. Irrelevant. Shear loads, two different basic kinds, the up and the down, and the twisting motion. Those are the two that I'm only really worried about. Those are the only two that I'm really concerned about explaining. So next up we have flexural moments, bending moments in these beams. And if I go back to my original beam design that I showed you from before, these forces on this beam cause a bending moment. So it's trying to bend downwards. You know, it's trying to. This is really difficult to demonstrate without pieces of timber that won't break. You know, without me breaking them, that will actually flex. Okay, so you probably find that the shape of a beam in flex under a bending moment is something like that. And in technical terms, this is a curve. So the top surface of this beam has technically gotten shorter because the radius has got shorter. So that top part of the beam, let's just do a close up. Because if these are the lines that are directed at the center of this circle, let's say, this line is shorter than this line. And if we draw a center line along the material, along the beam, then that is exactly the same length that it started out. It's the center. So by logical extension, because this has got shorter, the only way that happens is if it's in compression. This bottom surface has got longer, so it's in tension. So bending moments are technically a combination of these two working in conjunction with each other. It's that's the technical language that's the technical way of seeing it. It's you get a compression in the top part of the member, and you get a tension in the bottom part. And if we took a section through, that force would it would start off in one direction, it would come down across, So we would get two peaks, one at the bottom face, one at the top face, and then along the center line, the shear force would be 0. You know, if this line represents the 0 shear force, and this, yeah, I hope that makes sense. Again, I'm going into quite some detail. You know, I don't know whether this is relevant. Now, what I want to get at is that there are certain shapes that work best for these load types. If we're talking about tension, it doesn't matter. As I was saying at the start, it's a universal kind of benchmark for lots of different materials. There's only one mode of failure. So whatever shape member you're putting in tension doesn't matter. It's just about the surface area, and it's just about being able to transfer that force into all of it. For compression, we have, it tends, the member will buckle around its weak axis. So if you imagine we've got two axes, we've got one like this and we've got one like this. If one of those directions is weaker, then that's the direction it will bend in. And that doesn't necessarily mean whichever dimension is smaller, because in some materials, particularly something like this, which is plywood, we have it has different properties in both directions because of the way it's manufactured. You know, it's not a solid piece of wood. This is not the right piece of wood. You know, if we had this solid piece of wood is uniform in all directions. This is made of layers, so it has different properties. And I would imagine if I put this under compression, it would actually buckle in the long direction, which is actually unusual for this stuff. It would ordinarily it would buckle in its short direction. That's one of the unique properties of plywood. It doesn't actually come up that you get what's the word? Asymmetric. I can't remember what the word is, where the material has different properties in different directions. It's very unusual, but that's compression. It wants to buckle, and it's going to buckle in its weaker direction, whichever direction we calculate to be weakest. I'm not going to get into the calculations. Shear. Now, for this situation, we generally just deal with it with bolts. You know, it's not a big problem. There's no real risk of deformation. There's very little chance of failure. The bolts, when you cast a small piece of metal, you know, a big beam is actually difficult to maintain a very, very high quality of metal along its whole footprint. It's very, very easy to have weak points within that beam, and so the manufacturing of the beam has to be compromised in order to maintain those kind of pure standards. Whereas if you're dealing with something very, very small like a bolt, you can just make something in much harder material. So bolts are just incredibly strong. If you ever look at a steel beam connected to something else, it's only got like a few bolts in it, and you think, oh, that doesn't look like enough. Ah, man, those bolts, they've got so much strength to them, you just wouldn't understand. So for that sort of situation, we've got a column bolting to a beam, we generally don't worry about it too much. We can generally deal with it with bolts. Now with torsion, that's what this twisting is, this pure shear. This can cause quite big deflections because these steel beams, this steel, all materials don't really like torsion. If you imagine that sort of action, you know, that's quite a deformative action. It's very, very distressing to the material you're putting that force under. So what we tend to the best shape for torsion is tubes, whether a hollow circle or a hollow square. That's what we generally tend to use for things that are in torsion. And one other reason why we generally do that, if we go for this like a standard I-beam, and we try and apply a torsion on the bottom flange, for example, then what will generally happen is that flange will just deflect. It will just bend around this point here. All of that torsion won't get transferred into all of the beam. So we generally tend to use hollow sections because if you apply a torsion here, it really transfers it around. It's a really good shape. Now for bending moments, this is a consequence of this action here where I was talking about earlier, where we have high forces at each extremity, and that's how you end up with a I-beam size, because you want all of the material to be dealing with this peak of the force. That's what's doing all of the work. You get a real benefit from having depth. You know, you can, if you double the depth, let's just draw a beam that's double the depth is actually quite a big step up in beam terms. You probably get somewhere between 4 and 6 times the strength for the same I-beam. I've got a book of beams. I've said this before, and there are beams that are deeper, but narrower and lighter, and they've got like double the amount of strength for the material, for the amount of material in the beam. You know, if you have two beams that weigh the same, then they're using the same amount of materials, and then the strength is just a measure of how effective that beam is at supporting the force that you're putting it under. So deeper beams, much more effective, much more efficient. But you know, people don't want big beams in their houses. They want their head heights. So we use kind of shallower, heavier ones. That's kind of how it works. But that's why we have these I-beams, is because we have this peak force at the top and this peak force at the bottom, and we want some big chunky members to be able to take that force. You know, this part in the middle is really just there to connect the two together. That's really more or less what it's doing. I mean, it's doing a lot more. It's taking shear. I'm not going to get too specific, but the main job, the main thing that the structure of the beam itself is doing is taking that tension and that compression. So those are the things I wanted to discuss for structural basics, and this is mostly to do with individual members. You know, this is when once we've done the analysis and we come up with some forces for what, you know, if we put a structure in a piece of software, it will throw out a whole lot of numbers as to what a column is taking, how much force it's taking. It will tell me how much moment that beam is supporting, and how much torsion. It will tell me all of that stuff, and then from there I design these individual members, and that's where these things come in. It's the individual members. But what's sometimes more important to discuss is like the whole structure itself. So let's open up a new page. And I also think I want to zoom out a little bit because I'm about to bring in an object and it's quite large. So give me 2 seconds. There we go. I think that's about right. This is the edge of my table, by the way. If it doesn't line up, it's because I'm trying to line everything with this camera and it's really janky. So we have a box. Oh, that's still not enough. Hold on a second. Oh, no, wrong way. There we go. Okay, so we have a box. And a box is the perfect example of a complete structure. It's robust. It doesn't, it's for the fact that it's made out of cardboard, really, really flimsy cardboard. It's remarkably robust. The shape and form. Even though we don't have a side on this side, if you imagine a building is just a box. That's all it is. That's all it is. It's just that on a flat surface. But we don't like. We don't want to live in a box. We want to have windows and stuff in this box. So the principle of structural design is that every time we remove something from this box, we need to replace it with something else that replaces the same structural effect that this box has just on its own. So if we start cutting out panels, for example, let's just say we're going to have some windows in the side. Then we'll probably stiffen up this with some beams and some cross bracing. You've probably seen cross bracing in a building. And we'll stiffen this up so that all this single part of the structure from here to here will do the same work that the box was originally doing, and now we can remove these panels without consequence to a certain extent. In layman's terms, very, very basic. So whenever we're dealing with a piece of structure, and specifically a piece of furniture, I want you to be conscious that the situation that we want to end up with is a box. And if we don't have a box, then we need to strengthen that box in ways that replace the effect that the box originally had. From a structural perspective, these walls are too thin. If I can push on them, they bend. But all that is just a case of the walls being too thin. The box itself isn't deforming. The box itself is still structurally fine. It's staying solid. It's not moving. It's good. And this is the rationale behind which we design most buildings. I mean, particularly small ones. If you're talking about skyscrapers, bridges, stadiums, then you're dealing with a whole next level of engineering. And I don't have any experience with those. I have some pretty big structures under my belt. I've dealt some good jobs. I'm not an amateur by any stretch, but those you're almost, once you go into those sorts of big structures, big set piece structures, statement structures, then you're really dealing with the big boys. And you almost, if you get involved in that, then you become a specialist in those industries right from the get-go. And I always quite like general engineering. I always wanted to keep things loose. I wanted to have a wide variety of, I didn't want to be a specialist in one thing. I wanted to have experience in all of the things. So that's just a career decision, career decision we all probably make. But those are the structural principles that I wanted to get across. I don't know whether it's come across well. I don't really know with these things. You've got to imagine that this is my day job. This is what I do every day. So it almost becomes intrinsic. Like I don't have to think about this anymore. I go to a job and people ask me a question and I can just answer it on gut instinct alone because I've been doing it for too long. But hopefully it's given you some sort of taste for what I'm going to talk about, and hopefully going forwards, other videos, other jargon, other technical terms that I use will make a lot more sense. Hopefully that was kind of where I wanted to go with this. So that's it. Very, very straightforward. Hope it's been interesting. I very much doubt it's been very much fun. But till next time.